I wanted to point something out. It suddenly kind of dawned on me. Multiple requests have come in for like a summary of reactions. And so in the lecture, whatever it was, Monday, I pointed out that we had this summary slide for all of the fourth unit. And then it kind of like sunk in, well, not quite sunk in, because this is still missing the Sandmeyer reactions. So I said we needed this slide, and then this slide, slide 26 it looks like, has all the Sandmeyer reactions. This is all of our reactions from this most recent unit. And so we did that, whatever that was, Monday, and then Tuesday morning, I was just thinking through and was like, well, dang, why did I not do that for, I don't know, unit 3? And then it dawned on me that I did. There's the summary slide that has all of the reactions and all of the reactions and all of the reactions. So we've got 3 slides back to back right at the beginning of the lecture that covers technically not all of the reactions. But this covers 90% of the reactions. So there's a couple of reactions that didn't show up within this. So if you wanted summary of reactions, you had them. They were already there. I thought, well, maybe I didn't do it for Unit 2. And then I went back to Unit 2. And then scrolling through Unit 2, noted that I actually had done it for Unit 2 as well. So they're there and they're there. And then I thought about Unit 1, and I went, oh, well, they're there, and they're there, and they're there. So the reaction summaries have been provided. In full disclosure, they are not perfect. Okay, they don't cover all of them, but they cover the vast majority of them. One of the big problems within these reaction summaries is there's massive holes and gaps of knowledge within them, because only that single reaction thing doesn't specify all of the content explicitly within it, which is why we've got videos that then talk through the content behind how that reaction works. Okay, so if you need reaction summary slides, they're there. Okay, and I would recommend you reorganize them. Okay, and as the more I thought about it Tuesday morning, the more I realized back to fall of probably 16, I had a very, calling her angry is not nice, serious student that would sit in the back rows, and she had insisted that she wanted these big summaries and she wanted them at the beginning of all the lectures, which is why I conveniently went through and could look at all the lecture slides and go, oh, there they all are, because I'd done them for her however many years ago that was. So they're there, they're in the slides, and you should be using them. In the videos, they go through fast because we need to talk about the details behind each of those. So it's like, here it is, ta-da, this is the summary. Now let's talk about the detail behind the reactions, and that's what all those other subsequent videos are. So when we're looking for summaries of the reactions, I did say we talk about it for 10 minutes at the end because I had entirely forgotten that they were there. They're already there. Okay, so we will continue to go through them. And as we'll name drop, I apologized to Monique because Monique had pointed it out, and I said, oh, I'm not doing it at the end, I'm doing it as we go through, and she said that was more useful. So it's more useful to see it as we work through questions. What were those things that we needed to memorize and constantly refer back to? So what I would recommend you do is have these slides, okay, create your own slide deck, pull all of those summary slides out into one space so that now you can be reviewing those reactions. And when you go through and do an ACS question, reference back to it. Start that referencing process. Okay? Is that referencing process going to be fun and exciting and lovely? No, actually it's going to be horrendously miserable and you will hate it. Okay? But it's that process of, God, I hope I don't have to keep going back. I don't like going back and back and back. What's going to happen?
Well, then you're going to learn.
You will have memorized the reactions so that you don't have to go back and back and back and back. Okay? So it is the quick fix, here's the answer, that is causing problems because you aren't remembering the quick fix, this is the answer. It's only that frustration of getting things wrong and fighting through trying to find out why it is wrong that things start to stick. Okay? So, I just wanted to point out that those were there. You do have access to those. I will still try to summarize reactions as we go through and look at the ACS study guide. I also fielded another question from somebody else that was a very good question about, how should I prepare? What should I do? So let's go ahead and make sure everybody's on the same page on what you could do and prepare. Okay, if we look at the most recent ACS study guide, okay, what we've got is all of the material broken down into individual chapters that discuss each of those individual sections. The ACS exam covers everything. So you fully should expect questions from each and every single one of those sections. As a ballpark breakdown, when I go through and look at every ACS exam that has ever been written as a full semester, I think there's a little bit more than half what I would call first semester content. Okay? Other people would disagree with me, particularly when it comes into looking at, I can't believe they labeled it this way, our carbonyl chemistry. In our carbonyl chemistry, we're talking about our acid derivatives as well as our aldehydes and ketones. The acid derivatives, one of the most common ones being the carboxylic acid. And so one of the questions that appears within that second semester, quote unquote, section is ranking acidity. That's flipping OChem 1. That's not OChem 2. So there's a lot of stuff that gets called OChem 2 that is really just using fundamental building blocks back in OChem 1. Okay? So if you want to take my opinion on it, I think you're looking at probably 40 questions that are OChem 1. If you feel strong in OChem 1, look at OChem 2. If you feel weak with all that OChem 1 content, review OChem 1 to ensure that's square. Okay? You've theoretically had more time and practice with OChem 1 than you have had with OChem 2. Okay? Because believe it or not, the entire semester we've been doing OChem 1. We've talked about hybridization. We've talked about the number of bonds our atoms have. Okay? All of that is OChem 1. Okay? So if you have those fundamentals built out, all you're doing is scaling that up in slight difficulty for OChem 2. Okay? So that's kind of a first blanket statement. There's still a lot of questions to work through. Each of those chapters has probably 20 questions, okay, at the end. Where should you start? Well, you should start where you're weakest. Do you know where you're weakest? I'm going to take silence to mean no, you don't know where you're weakest. Okay, that's fine. Okay? They each have 20 to 30 questions within them. Okay? Flip to the section within each of those chapters where it just lists questions. Okay? You don't want to look at explanations because the explanations, as much as you try to, you will see the explanation and that will influence how you answer. So don't look at those. 5 questions within each of those chapters. Okay? You could probably get away with the first 5 questions. I don't know how they've structured it, if they've put it in chronological order or if it's just random. Okay? But pick 5 questions within that chapter. Okay? You're only allowed 1.5 minutes per question. Okay? So your 5 questions, set up a timer, 7.5 minutes, go. Do your questions. Okay? You've got answers. After that 7.5 minutes, go back and look at the answers and see how well you did. If you got 4 or 5 questions right, okay, that's a pretty solid area. You probably don't need to study there very much because you already know it pretty well. However, there was probably content that you memorized. So as you were going through, you're like, oh, I know this fact. Write that down. You've got a memory list. Put a memory list down next to you and write down that fact that you memorized. Okay, add it to that list so that you can now go back and review that list. Okay? You go through and chapter 1, you get 2 or 3 questions right. Okay? That means you don't know it as well as you think you do. You need to go back and review. How you do review is up to you. Okay? My argument with where we're at right now, we've still got a little bit of time. You could go back, reference the chapter, reference lecture videos. Okay? Play lecture videos at double speed. Okay? A request was made for practice smart work. Do practice smart work questions. Okay? Do the practice within the ACS study guide. Okay? Again, try to leave 5 questions alone. Not the same 5 that you started with, but pick another 5 and say, I'm not going to look at those 5 questions. Okay? Once you've done that review, go back and now try those 5 questions again. Okay? Theoretically, you're improving. Bless you. If you're not improving, that requires more review. Okay? More practice. You may run out of questions within the study guide. Again, smart work. Practice exams. Okay? I can provide access to the old practice exams from OChem 1. So you've got those at your fingertips. Make sense? Okay? Move to the next chapter. Same deal. Same process. Kind of makes sense? So you should be able to cover all of those chapters to get a feel for now where you're weak, where you're strong and where you're weak. If you're hitting 4s or 5s, okay, that's pretty solid strong. If you're hitting 4s and 5s with everything, I would question how well you actually took those questions. Like where the answer is already bubbled in, okay, were you getting help? This isn't a get help, this is a self-assessment. Don't do it with somebody else helping you. Okay, 7.5 minutes. Don't take longer, 7.5 minutes, do the best that you can. Okay? So we said 4s and 5s, 2s and 3s, that also leaves the 0s and 1s. If you're getting 0 and 1 in that chapter, this sucks. I apologize. That's a lost cause. Okay? It does depend on the rest of the system. If you've got one lost cause chapter, okay, yeah, study that chapter. Okay? And don't stress as much about the other ones. Okay? But if you've got multiple lost cause chapters and multiple 2 or 3 chapters, you should keep your focus on the 2s and 3s, and you should leave the 0 and 1 chapters alone. Okay? It's 16 chapters. You're going to have to decide kind of where your thresholds are for that, because that then brings in kind of the last aspect behind this that is very, very challenging to deal with. What if you go through and do this and 10 of those 16 chapters are 0s and 1s? What if all of them are 0s and 1s? I don't know. Okay? That's now a very hard decision on your part. You've got to decide. Okay? What that assessment means is that you know none of that content. The odds that you're going to score well on the ACS, regardless of the amount of effort that you put on behind it, is not going to be very high. Okay? And you're probably looking in that guessing range. Is that guessing range, does that match what you need to get whatever letter grade you want in the class? If it does, I still argue it's a roll of the dice. Roll the dice and see what happens on the final. Okay? But if that guessing range, 70 questions, 25%, 14 questions right, is 14, does that get you what you want in the class? You should consider withdrawing. Okay? And that sucks. Okay? I know from experience. I withdrew from OChem 1 the first time I took it because I was doing horrible in it. Okay? It's not a pleasant experience, but it's not the end of the world, and you can come back and you can fix that in the next time around. That means making changes to how you approach this semester. If you didn't get the help that you needed this semester, next semester, when you come back and take it again, get the help you need. Okay? Seek out the people that can help you. Okay? To that end, if you take it next semester, number one, you cannot take it with me because I don't teach it. Okay? But you can still ask questions of me. I have no problems with that. Okay? You move to Montana, and you're taking it in Montana, but you don't like the teacher there, and you don't like me either, but you rather communicate with me, send me an email. I don't understand what this is. Okay, I'll do whatever I can to help you. You are a lower priority because you're not my student at that point, but I will absolutely do whatever I can to help you. Okay? Kind of, sort of? Got a rough plan? Okay, I'm really nervous about just spinning open the ACS book because the last time I spun it open, it hit all the chirality stuff, and I hate that. Do we have a section we would prefer to look at that was not chirality? Because if you want to be a real jerk, you just be like, I want help with chirality.
Is there like, not that I have to look out right now,
Yep.
but is there something that like we're all collectively missing as a class, or that we're like, is there a section that you see us failing at strongly?
What I see is definitions. There's zero application of the definitions. So when I say acid, you can tell me, oh, it's a proton donor, but then you can't draw a structure to say what a proton donor looks like at all. There's very little application to the memorized fact. And that is the hardest part in OChem. It's not just memorizing a reaction. I have to be able to apply it to this foreign-looking structure. So you have to have selective vision to recognize what those pieces are. So when we say proton donor, okay, what is a proton? Well, a proton was an H. That proton had to be partially positive, which means that proton needs to be bonded to something partially negative. What would be a good thing that was partially negative? Okay, chlorine, we now have an acid. Okay, OChem 2 makes it more complicated because that's ultimately a Gen Chem definition of acids. That's okay. Bond it to an oxygen. Is it an acid? Well, I don't know. If that's all it was, then I would have OH minus. Is that an acid? No, the reactivity isn't the positive hydrogen. It's the fact that I have a formal negative charge on the oxygen. You have to weigh the balance of both of those pieces of information. Right? So if we want to talk through weaknesses, the biggest weakness is applying each and every single one of those definitions, which is why every time we go through in class, we look at a structure and we say, how does this act? We apply the definition to that structure so that we can say, this is how it reacts, this is how it moves. Okay? That is one approach to OChem. And full disclosure, that is very challenging to do. That requires lots of practice to recognize those patterns to navigate through. Right? Where is that practice done? And that could be another follow-up question. Well, I'm doing all the smart work. Doesn't that mean I've done enough practice? Smart work does not give you enough practice. Smart work is a skeleton structure to provide you enough to say, do you know what you're doing? Are you getting it perfect on your very first attempt without seeking out outside help? Then yes, you know what you're doing. Did you seek outside help? You don't know what you're doing. You need more practice. Find more questions. Right? I had tried to build smart work at one point in my existence as an educator as all the practice you need. What becomes the problem with that? Say that again? It's a lot of work. Okay? And I got aggressive pushback from students saying this was way too much work for them to be able to complete, and I completely agreed. So what I went through and did with the smart work was ultimately remove all of the building questions with the intent that we would talk through those building questions in class as you looked at things. Oh, I don't understand how this works. Okay, let's look at how that builds so that we can then apply that to a more complex system. Okay? That takes time. The other approach, rote memorization. Okay? Rote memorization of the reactions that are there. Okay? We've gone through several examples of that in class. The class isn't doing rote memorization. There's really only two approaches, rote memorization and application. That's it. Okay? If there's another one, I just don't know what it is. Okay? And if you aren't doing either of those, I don't know. Okay? So to me, when you say weaknesses, those are the two weaknesses I see. I see two paths through class, and I don't see anybody, or the vast majority of the class, not doing either of those branches. You gotta, and you don't have to pick one, you can do a crossbreed of them both. But those are those weaknesses. To me, all of those things are addressed in OChem 1, that first term material. So a good place to start would be looking at first term stuff. Do you understand what's happening within those? If you don't, that's going to make OChem 2 that much more challenging. This is why, and I told OChem 1 people this, I think in OChem 1, the historic trend for grades as you move through OChem is downward through exams. Because what happens in the very first test, everybody memorizes without applying or understanding what's happening, and then you move to the next test and you're not memorizing one test worth of content, you're memorizing 2 tests of content, which means you start to falter. By the time you hit OChem 2, you're not memorizing 1 test of content, you're memorizing 4 tests of content, because OChem is not a 2-semester course. It's a 1-year course that has been arbitrarily broken into pieces. Okay, so you have to constantly pull that content back up. That sucks. But there's literally no other way to do it.
Can we look at chapter 14?
Sure. What's chapter 14? Okay, enolates. Would have helped if I looked at the page number.
Do you want me to hold it open for you?
No. Seriously? You're really gonna do this to me? Yeah. Well, hope for the best. Chapter 14, we're talking about enolates. What are our enolates? Say that again? Okay, our enolates are actually encountering a couple different spaces here. With an attempt to color code. Your enol is with the hydrogen on it, so it's our alkene with an alcohol directly attached to it. Those 2 functional groups interact with each other. That interaction creates a new functional group. That's our enolate. Okay? Officially, if we have an alcohol next to an alkene, it's not an enolate, it's an enol. Okay? But because we know there's a large difference in electronegativity between the oxygen and the hydrogen, that hydrogen is acidic, and under basic conditions, I could deprotonate that hydrogen. And if I removed that hydrogen, the electrons would go to the oxygen, and what we would form would technically be the enolate. Okay? Just to be kind of extra clear within that system. As long as you're aware of those connections, when we're talking about our enolates, we're almost universally referring to either one of those states and deciding which one specifically has to do with the conditions. Okay? If we're going to see the enolate, we have to be under basic conditions, because basic conditions need to remove that acidic hydrogen. The enol would typically be your acidic conditions, because you're keeping the hydrogen on the structure. Okay? So what we're concerned about is the oscillation back and forth. Sorry, not back and forth yet. Okay, but dealing with our enol or enolate, depending on how you want to address it. It's way too crowded for me, so I'm going to erase it all. And what is the big content piece that we should know about our enol? That's actually kind of a lie. There's 2 content pieces. I'm just going to say tauto. It can tautomerize back to the carbonyl. Okay? Because it wasn't super clear as to what was out here. Okay? Those could be R's. And those R's could be, well, for sure the one on the left has to be a carbon. Why does the one on the left have to be a carbon? The R on the left has to be a carbon, not a hydrogen, because it has a pi bond. Okay, it has 2 bonds to it, so it would have to be there. Okay, but the one on the right could be carbon or hydrogen. Okay, so I guess we could get a little bit more clear and say this could be a carbon, or has to be a carbon. And then that R group could be pretty much anything else. Okay? It typically is referencing just carbons and hydrogens, because if it referenced another oxygen, we're now changing the functional group. So when we are using R, the point of R is to not change the chemistry of the primary functional group we're looking at. Okay? So the big thing that we should be knowing about our enol chapter is that we get this tautomerization process. Typically, the part that's important isn't the enol, because the enol is not stable. And the vast majority of the time when we go through and look at our keto-enol process is it heavily favors the keto or our carbonyl form. Why is that relevant? When we look at any of our questions, typically what are we going to see? We're going to see that keto-carbonyl form. We will not see the enol form. We need to be aware that the enol form is possible and it can drive a lot of secondary chemistry. So what we see is this given structure, and we are responsible to kind of know, I guess, that the enol can come about. Well, why do we care that the enol comes about? How is it reactive? It is reactive because if we look at a resonance form of this, we can put those electrons of that pi bond sitting squarely on that carbon. That becomes super important to us because that is now a carbon nucleophile. So when we talk about enolates, the important part isn't necessarily that we can form these enols. That's not a big deal, okay? Because the enols aren't particularly stable. What's important is that we make a carbon nucleophile. So when we look through all of these reactions, we're going to expect to see tons of carbonyl compounds. And what we're looking for is a carbon next to that carbonyl. If I have that carbon, does it have a hydrogen that could be removed? Why do I need to remove a hydrogen? That's how it's going to make the alkene of our enol. So we could layer a little bit more information on this. I have to have that hydrogen. That hydrogen becomes so important that we name it. We call it an alpha hydrogen. And the alpha hydrogen is acidic. And it is acidic because of the resonance structure with the enolate. There's our keto-enol process. So all of that is really just saying I have an acidic hydrogen. That gives me a carbon nucleophile. What can I do with a carbon nucleophile? React it with positive stuff. Okay? The rest of the system now is what is the positive stuff you want to throw at it. Sometimes the positive stuff is obvious, sometimes it's not. Okay? So if we want to talk about core memorization things, how do I want to tweak this? I think it's going to hurt me to do this, but I think this is okay. I have a hard time with those arrows in there. We'll draw a little squiggly line saying similar. Okay. If we have our carbonyl with an acidic hydrogen, with a hydrogen at the alpha position, that is roughly the same as saying I have that structure in blue, which is a carbon nucleophile. Kind of, sort of? Okay. There's chemistry, there's arrow pushing, there's all of that goes behind it. Okay? What bases do you use to remove those hydrogens? All of that goes with this. Okay? But that becomes kind of the core fundamental building block, if we will, for looking at this chapter. So, that very first question, I would argue, is kind of a rough one, but I think we could probably pull it off just based off the information we addressed. Okay? Right out of the gate for that first question, what makes this question challenging? Fair point. I hadn't looked at that. If we go through and look, each of our answer choices are written in a formula format. That's obnoxious. Right? If you don't like that formula format, that's okay. You should draw it out. Okay? For me personally, it's not bothering me because what did I remember? My carbonyl and acidic hydrogens. So I could go through and look. Let's see if I can color code this match. Carbonyl, acidic hydrogen. Whoops. Carbonyl, acidic hydrogen. Carbonyl, no acidic hydrogen. Carbonyl, acidic hydrogen. Okay. We're cheating because we're in the enol chapter, so we know that context has to somehow be relevant. Okay. By just looking at carbonyls through our answer choices, the enol should be sending off alarm bells. Right? That should be a red flag right out of the gate. If I'm seeing carbonyls, I should probably be considering this enol thing potentially being a thing I've got to evaluate. Okay? Why else is it challenging? This is for you because you complained about exam 2.
Because there were so many. Tell me there were not so many.
There were a lot. There's a not within this, so we've got to be careful within that context. Right? So that not is going to mess with our system. Right? Another reason why I think it's challenging, aldol reaction. What the hell is an aldol reaction? If that's your response, that's why this question sucks. This is why you don't see this kind of question written by me. Because that has required you to memorize what an aldol reaction is. That's obnoxious. Okay, does the ACS do that? Absolutely, because that's part of organic chemistry. I disagree with that part, so I don't test as heavily on it. Right? But let's say you don't even know what an aldol reaction is. You know reaction. Well, to run a reaction, what do you need? All reactions have these. I need a positive and a negative. So I can go through and look at all of the answer choices already given. Do all of the answer choices already given give me either a positive or a negative? Yes. Where's the positive? The carbon of the carbonyl. Because I acknowledge that when I see a carbonyl, that there's a resonance structure that puts a positive charge on that carbon. There's my missing octet, I've got a positive. But to run a chemical reaction, not only do I need a positive, what do I need? A negative. We go, oh, could the oxygen react as a negative? The oxygen doesn't react very well as a negative. Why? This one's hard, but this is why we talked about this functional group. Those electrons are on an electronegative element, and they're preoccupied already with stabilizing the carbon within the structure. Can you force it to react with another positive carbon? Yes, you can. It's challenging. It's a named reaction. It's named because it's not likely to happen. Okay? So cool, I've got a positive, I don't have a negative. Okay? How could I get a negative? You said it. You did. I have an acidic hydrogen. What does it mean if I get rid of that acidic hydrogen? What do I generate?
A carbon nucleophile, a negative, that would give me a negative and a positive. So if I had a negative and a positive, I already know I have positives with the carbonyls. All those answer choices give me that. All I have to find is a negative carbon. If I have a negative carbon, a reaction can happen. Is it the aldol? I don't flipping know, but it's the only choice I've got. 3 of my answer choices all have acidic hydrogens, which means all 3 of those answer choices could give me a negative carbon, which means all 3 of those could do a reaction. The question says cannot, which means answer choice is B. Do I have to know what an aldol reaction is? No. What I have to do is understand some of those fundamental definitions and work with the information I have at hand. Not just saying, damn, I don't know what an aldol is, guess. Kind of, sort of?
Yeah.
Should we actually draw out the aldol?
Okay.
Yes.
Yeah.
You guys are jerks.
All right. It's crazy if I asked.
I know. Which one do we want to do an aldol for? You got to pick one. A, C, or D?
D.
Thank you. That one's probably the nicest of them.
That's what I chose.
CH3, I don't care about the CH3. What I care about is my acidic hydrogen. Whoops. Stupid drawing system. So I can draw my acidic hydrogens, and then I've got my carbonyl hydrogen. I already knew I had my positive carbon through a resonance system. But the big deal I need would be that negative carbon. Right? How do I do that negative carbon? Well, it would be useful if I had, I don't know, maybe a base. Well, look at that. The reaction said I had a base. So I throw in a base. What does the base need to do?
Acidic hydrogen.
Donate electrons to an acidic hydrogen. Do I see an acidic hydrogen? Yeah, I conveniently do. Okay, I could go ahead and pull it from this one. I'll put that hydrogen up there so it's out of the way. There's my negative. Okay, now what happens? Well, I have a negative and I have a positive. What should I do? Link them together. Sorry, I inverted that. H3C, CH, carbonyl, hydrogen, purple bond, red carbon, oxygen negative. Whoops. Try and draw it as close to the system as possible. There's 6 lone pairs on that. I'm out of space. Negative. CH2, CH3. What can happen? Would this be my final product? I know it's really small at the bottom, so you can't tell. It's negatively charged at the bottom. It shouldn't be negatively charged, so what should I do? I should protonate. So if I go through and protonate this, what do I have? I have my CH3 connected to this CH. There's my aldehyde. There's my new purple bond to my red carbon, hydrogen. I protonate, there's my alcohol, CH2, CH3. CH2 looks like a CH3. Say it again? I know, but I didn't do it over for that one, so. Right? Is this the product? Is this now an aldol reaction? What's the name of the blue functional group? An aldehyde. What's the name of the red functional group? An alcohol. What did I just make? An aldol. There's your aldol reaction. Didn't even need to know it. I just put negative and positive, jammed stuff together. Oh, look, it what are we going to call it? Let's call it an aldol because there's an aldehyde and an alcohol in it. Yeah, it's because that's roughly the level of educated thought that went through that, or that naming system. That's the point of that process. You find a negative, you find a positive, you put them together. The only way we find negatives and positives is by applying those definitions. Does that help?
Yes.
Okay. There's a complication with our aldols. What's the typical complication of our aldols?
Would it be steric injury?
No. There is a reversibility behind this that does typically come into play. But if you're being asked for aldol, they're okay drawing out the aldol product. The complication that I would throw into this is that we still technically have an acidic hydrogen, and arguably that hydrogen is more acidic than where we started. Aldol reactions, largely due to that secondary acidic hydrogen, are very hard to stop at the aldol. And what will typically happen is a base comes in, removes that hydrogen, making my carbon negative again. I need to find something positive nearby to stabilize it. Oh, there's a carbon here connected to an oxygen. That carbon is positive. Those electrons could swing down, kicking out OH as a leaving group. Meaning, what have I done? Whoops. No longer a CH. There's the word. What we've done is a condensation, because what we eliminated was water from the molecule. I keep doing that 3. Jiminy Christmas. CH2,
What?
CH3. So typically when we look at our aldols, we very commonly get the condensation following along afterwards. That has to do with the chemistry that started the whole cascade to begin with, an acidic alpha hydrogen, which allowed us to get to an enol. There's that whole chemistry process coming back full circle, continuing our push. Okay? Next fun thing behind this, if we were asked a multiple choice answer, would our multiple choice answer look nice and drawn out like this? No, it wouldn't look like this at all, because what this shows is the proper arrangement of the atoms, allowing us to see the chemistry behind it. Okay? That is actually a horrendous way to draw that molecule because it's not the lowest energy conformation. And when we look at our answer choices are very commonly, though not always, drawn in the lowest energy configuration for this structure, which means we need to be looking at a zigzag structure. If we're going to look at that next level behind this, let's see if I can pull this off. 1, 2, 3, 4, 5. 1, 2, that's 3, 4, 5. Position 5, I have a carbonyl. I don't know why I numbered it that way because that's numbered technically incorrect nomenclature-wise. 2, 3, there's our double bond. Position 4, we have a methyl. That would be what I would expect to see. Make sense? If they want to get really obnoxious, what could they also convert that into? CH3, CH2, CH. They might even go this far. That would be really annoying. They'd probably say CH3, CHO. So they could go all the way to that formula state. You're responsible for being able to convert out of the formula into the structure. Okay? Typically, I've seen it drawn out this way. Hooray?
Hooray.
Hooray. Oops.
That helps understand.
Last thing I want to throw out here. Maybe something that you're just like, God, I just need something to memorize, Mike. That was an awful lot of stuff to have to draw out to memorize. I'm getting a little too specific there. What the heck are you drawing, Mike? I'm taking one aldehyde or carbonyl compound, and I'm putting it on top, and I'm putting the other one down below. Note, what am I aligning directly underneath each other? The carbonyl, what charge was the carbonyl? Positive. What charge did that carbon become? Negative. What could I do? There's my aldol condensation. It's a full delete of the carbonyl, and I replace it with a carbon-carbon double bond connecting those two carbon chains. Okay. Perfectly fair cheat. It requires that you memorize that aldol means this, and technically aldol condensation means this. It's a very niche response that you could use. Sometimes it works, sometimes it doesn't. Okay? For the particular system that we just addressed up at the top, would it have addressed? Would we have been able to figure it out? Potentially, as long as we acknowledge that what had to happen was the loss of those two hydrogens, okay, from our alpha position of our carbonyl. So just memorizing aldol means this structure isn't useful. What's important is to recognize what we got rid of to make this structure with the aldol, and then that would have helped us. Does that make sense? Those of you saying, that's pretty useful, I wish I had known that, I did tell you that. It's in the lecture slides. I don't want to erase that. Moving to the next question. This question's a little bit different from the first question. The first question just said which cannot be used, which means to answer that question, you have to look at your answer choices. You don't get the privilege to ignore the answer choices. Okay? That becomes challenging because in that context, you are now having to look at wrong answers to answer the question. That's problematic. This question, which reactant can be used to make this compound in an intramolecular aldol reaction? That's a whole lot of flippin' words, okay? But I've got the product. Can I reverse engineer the product into a reactant? If I feel yes, I don't need to look at the answer choices. I just look at this structure and reverse engineer it. I'd memorize this little pattern, right? Yeah? Find those pieces in that structure. They're all the same color, so let's see if I can color code a little bit. The dotted lines, I know this is confusing, the dotted lines are referencing the things that were lost to make the solid line structure. Okay, to make our final aldol product. So when I look at my final aldol product, how many carbonyls do I have? One. The bottom carbonyl was dotted line that was lost. I look at the final product. The final product has how many carbonyls? One, which means what color should that carbonyl be?
Blue.
That one needs to be blue. Okay? From that blue carbonyl, there are two carbons that connect it. One of those is the carbon relevant to our aldol. The other one is the R group. 50-50 coin toss. Which one is it? For those paying attention, it's not a 50-50 coin flip because I know the blue one has a double bond connected to it, which means the carbonyl up here, that's my blue carbonyl. What does that mean? That double bond is now what connects to my purple structure down below. Which means what do I need to do to reverse this process? Break that bond. Okay? And if I'm going to break that bond open, what happens? That blue carbon needs what? What does that blue carbon need? It needs 2 alpha hydrogens. It already had an alpha or a hydrogen there, so it's a CH3. What does the purple carbon need?
Wait, carbonyl.
The purple carbon, okay, in that structure is right here. That needs a carbonyl. What's to the right of my carbonyl carbon? CH3. What's to the left?
C,
CH2. What's to the left of that?
CH2,
What's above that?
CH2,
What's that connected to?
the carbonyl, or, yeah.
There's the answer. What's that?
That's C again.
What? Not according to smart work.
Yeah, that's C.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4.
Carbonyl.
Smart work is fine with that. Jiminy Christmas. If you want to see the extra carbon, you can drop the extra carbon in there. We now have the answer. What do we need to do?
Decide which answer matches that.
It's now just a question of taking this answer that we've drawn theoretically on scratch paper, okay? I would argue even theoretically on our tracing paper, and then what I could do is now pull this aside, which I can't do easily. I'm going to have to erase my structure, and now I can look at my answer choices. Conveniently, all of those answer choices are not shown in the cyclic format. Why not? The cyclic format isn't the lowest energy form. We have to straighten that chain. So now what you're trying to do is just match the structure that aligns to this.
Okay, well, D is wrong because it has 2 carbonyls, so we take that out.
It is B.
D has 3 carbonyls, which doesn't make any sense. We should only have 2 carbonyls. Okay? The rest of them you might be trying to go through. I would just count. Okay? So my structure has 1, 2, 3, 4, 5, 6, 7 carbons. So I would just start counting through. Actually, as I do that, I would eliminate C because that has an ethyl hanging off of it. B has 7 carbons. Okay? A I would eliminate because it has that ethyl hanging off of it also. Make sense?
Yes, makes sense.
This is using the pieces of information we already had memorized. If you haven't memorized those pieces, have you started your memorization list? Okay? And if you haven't started your memorization list, all I'm trying to do is point it out. You don't have to do what I asked you to do. That's fine. Oh, that's 2 pieces.
You dropped his pen. And it broke.
I got a little bit of glue for that.
No, the tip broke. I've thrown it too many times. No, like it's broke. So if I'm lucky, I can keep it on there so it'll function.
Can't
We'll
you
see.
just use your finger?
I can. I have fat fingers. I've done it before. It doesn't work well.
Well,
Okay.
what about like a different, go ahead.
So, we good with that one? Or questions?
No, makes sense.
Stop doing. Wait.
Wait, what?
Take a picture? Okay. Not that one. We still good to roll through our enolates?
Yes.
So here's our next question. Same process that we should try and do as we did for the first one. Why is this one an obnoxious question?
It doesn't even give us a.
Oh, actually, lots of things why it's obnoxious. Actually, the not, I think, immediately sets it up to be super obnoxious.
What is
Because
knots?
it's a not, we have to deal with knots, and
It doesn't give us a structure.
yeah, we have to look at the answer choices to answer the question.
Okay. I'm gonna much is a new pen? $500.
You don't have to get a new pen.
I don't have to do that. I just got tape.
Or E6000.
That's great. Someone get my new pen for Christmas.
And my father-in-law was like, "Dude, I hate shopping you for Christmas. You don't want anything." I'm like, "Yeah, don't freaking buy me anything. Leave me alone."
You don't like presents?
New pen.
My list is so long and detailed.
Ask for some tips.
Well, now I got something I can ask for, yeah. Okay, so what is not a step in the mechanism of the aldol, which means a couple things. Number one, we had a cheat, right? Is this cheat going to work? Nope, we have to know the mechanism. We have to know the order in which it runs. Okay? So depending on what you have decided to do with your approach, do I understand the whole process, or am I just memorizing key pieces of information and praying I don't see these questions? Okay? If that's your system, then all you do is guess. Guess and move on. Okay? You could go through and take a kind of an educated guess by looking at the individual pieces and hope for the best. Okay? But your time spent should be very, very, very short.
Oh, well.
If all you've done, you're trusting whoever bubbled this in. So I'd be very careful with that. No, I borrowed this from the tutoring center.
You stole this from, I borrowed it.
And the tutoring center got it from a former student. So a former student could have answered it correctly. I honestly, I don't know. I haven't looked at it. Okay, so we're looking at not a step in the mechanism. Right? If we're looking at the reaction, what did we need? What were the two critical pieces that we needed to run the reaction? A positive and a negative. The positive was there from the beginning. Was the negative there from the beginning? No, we had to generate that negative. How did we generate that negative? We removed an acidic alpha hydrogen. That looks like step A. Right? Step A is generating the carbon nucleophile to run the reaction. I need that step. That's pretty critical. Are the arrows wrong? No. So not only is it doing the right thing, it also has the correct arrows. That is a valid step, which means not the correct answer that I want, because I want the not. Right? We could move to B. What's happening in B? Carbon nucleophile attacking a positive. You mean a negative carbon attacking our positive carbon? Is it the negative carbon we wanted?
Yeah.
Yeah? Is it the positive carbon we wanted?
Yeah, well, it's in the middle. Yeah, it's in the.
Yeah. And if we think through how our reactions ran and how we talked through it, you might be, but Mike, you didn't show it this way. Okay? You're correct. If we think through how we look at our reactions, when I talked through it, what we talked about was our negative carbon coming in and attacking our hydrogen carbonyl, our group H. Does that look a little bit more familiar to you?
Yes.
Okay. That's exactly what B is showing for the most part. Okay? Why is B better than what I just drew above?
Well, it's like putting resonance between carbon and oxygen.
The relationship between this structure and this structure is resonance. Okay? And when we draw out mechanisms, which structure should you use? The best. Between those two structures, which one's the best? The negative oxygen, because I'm putting the negative charge on an atom that can hold the charge better than the carbon. Okay? Why did I opt to not show that when we talked through it? Because what I wanted you to see was the chemistry following our reactions. We talked about best and useful. The useful ones allow us to move through the chemistry. The best ones are officially what ACS is going to look for. It's officially what smart work looks for, which is why you've had the practice with those. What does that mean for answer choice B? It's also not it. What happens in C?
B.
You protonate. Did you need to do that? What happens if you protonate?
It gets rid of the,
lose
well, it gets rid of the negative charge.
Right? That's what you would get if you protonated?
Yeah, yeah.
Dude, we don't want to protonate. What was the name of that functional group? An aldehyde, what's the name of that functional group?
Alcohol.
An alcohol, what did we just make? The aldol, what mechanism were we trying to do? The aldol mechanism, did we need to protonate? Yes,
Yeah.
yes, we did.
Yeah. So it's D.
Okay. Oh, so it must be D. Okay. Fair. Why is it D?
Well, because all the other answers are wrong.
Okay. Acceptable on the exam. Not acceptable now.
Okay, yeah, well, yeah, we have to explain it. I guess it's because the oxygen is being bonded with the carbonyl carbon, which isn't like stereotypical to the type of reaction.
That's a little bit better. When we run the aldol, it's a negative carbon reacting with a positive carbon. Is that what D is showing? No. That's why D is the right answer. D is taking the negative oxygen and reacting it with the positive carbon. See the patterns?
Yes.
Right? A lot of these things should be followed through this same process. You start with A and you work your way through. Okay, well, oh, but D was the right answer. I wasted all that time. Theoretically, you aren't wasting your time because you're looking at that and quickly processing where that aligns to what you know. And if you're looking at it like, I have no clue, then it doesn't matter where you start. Just pick a random spot. Sometimes maybe you'll be right. Other times you'll be wrong. Just like if we started with A first and worked our way through. Make sense?
Mm-hmm.
Okay, I don't know that we've got another question within this. Look at that. I feel like you're mocking me.
Stupid.
True, but it's appropriate.
Why? Don't be so hard on yourself. They're making fun.
I think it was an appropriate response. Okay, what is the major product of this reaction? So we could crunch through this most reactive thing. I'm perfectly okay with that. Okay? You could also look at it and be like, but Mike, this isn't an aldol. Yeah, it isn't an aldol, but it's the same chemistry. And because it's the same chemistry, we should acknowledge it as the aldol and just not worry about it. I don't care that the name doesn't perfectly align. Is the chemistry still the same? Yes, it is. Right? Do I have a carbonyl? Yes. Do I have an alpha hydrogen with acidic hydrogens? Okay. Do it. For the record, I can't believe this tape worked.
Tape's been working for everything today.
Yeah, it's pretty awesome. See if I can get a sponsorship. And it's Scotch tape.
It's perfect for Christmas presents too.
Oops. So we're taking our structures, we're roughly aligning them into that formation, and we're going to try and run our system. This is one we probably need to be a little bit more careful on, because if we just outright run the memorization trick, what happens? We delete those and we connect across. And we're starting to get this very strange functional group in here. the oxygen directly connected to the alkene. Okay? But if we did that, I'm actually kind of curious. Let's see if that was one of my answer choices. Ooh, it was not. What does that mean? I missed something through that process. So this would be, if all I did was memorize, I need another thing to memorize to match this particular structure. Okay? But if I'd understood the process behind this, I do one hydrogen at a time, breaking each of those bonds. So, oh man, I gotta erase the whole flipping thing. Draw it upside down. We delete one of those hydrogens to make one bond and break one of the oxygen bonds. Have I memorized anything particularly special about that red carbon now?
Oh, you mean the, sorry.
Is there anything
Actually, look, it's partially positive, is that what you're going
It is
for?
partially positive. We still formally have this bond. Those electrons went up to that oxygen, making the oxygen negative. Tetrahedral, is that sending off any alarm bells for anybody else? That should be a tetrahedral intermediate that we spent the last 3 weeks talking about. Right? As that tetrahedral intermediate, what happens? Instead of protonating that oxygen, what happens? Those electrons swing back down to reform the pi bond and eject. Our oxygen is a leaving group. We still have that acidic alpha hydrogen, but there's nowhere it can really go. I can't do now an elimination, because at best, if I removed that acidic hydrogen and have that negative carbon, what could those electrons do? Well, they can resonate, but I'm not breaking any sigma bonds. And they could resonate the other direction. Same deal, I'm not breaking any sigma bonds. Okay? So for this particular reaction, it stalls there. And I don't lose that second hydrogen. This comes about if I've added an extra thing to memorize. Okay? And I'll add that here in a second. Or it comes about recognizing how the mechanism works and recognizing where new patterns come into play. That red carbon before the reaction ran was a hemiacetal. Hemiacetals, we should remember, are unstable and quickly revert to their carbonyl state. So we've got some more things that we could throw in here, because what we're talking about is our acetals. Acetals are in equilibrium with our hemiacetals and favor our carbonyl. But those are all equilibrium reactions that generally favor the carbonyl state. So as soon as I have that kind of intermediate structure, I've got a red flag that I've memorized already, and I can overlay that information in and shuttle that in. Or I memorized, I don't think I have enough space to squeeze it in here, but we're going to try it anyway. I memorized a Claisen reaction. And in the Claisen reaction, I draw the exact same stupid flippin' thing that I would do for an aldol, except I have this one extra little piece out here, calling it an ester. Just deleted something. And in the Claisen, I form the new bond. Whoops, nope, I did that right. I gotta orient my structures. Here's my carbonyl. CR. OR. In the Claisen, I form the new bond here. I get rid of that alpha hydrogen, and I get rid of VOR. Okay? That should look very similar to the aldol, and that's because it is. There is an added complication that you could memorize within the Claisen. The Claisen requires that there's 2 alpha hydrogens for it to actually run. Okay? There was a test question explicitly on that. Okay? Will ACS ask about that? I don't know. Okay? But that's now a nuance behind it because the cheat, again, isn't going to set us up with that, and that's really digging into the mechanism that we definitely don't have enough space on the board to go through and do. Okay? But what we now have is our proper structure up at the top, and now what we're trying to do is match that to one of those answer choices. Again, we have to deal with the whole drawing symmetry issue stuff. Okay? But at very least, what we could try and do is cheat. I have an ester, and I have a carbonyl, ultimately a ketone. This is a diester. That one's wrong. This one doesn't have an ester. This one doesn't have an ester. That leaves only one answer choice, C.
Okay.
And if I've got the structure, I can now start to make those patterns. If I know my functional groups, I can start to make those patterns. If I don't know the functional groups, what I have to do is count up all of the connectivities between that to try to align them with those answer choices. That is not an easy process to do. Okay? We're Wednesday, right?
Yep.
Before you all take off, and I'm going to stop recording for this part.